Welcome to Grade 10 Chemistry. This video was produced by E. Fanos. My name is Jessica and I'll be your instructor for this unit. Unit 4, Chemistry in Industry and Environmental Pollution. In this video, we'll be going over Subunit 4.1, the introduction to this unit. By the end of this subunit, you should be able to list general characteristics of chemical industries. A chemical industry is an institution involved in the production of chemical products. Chemical industries use naturally available materials to produce the desired product. They involve chemical reactions and consume relatively large quantities of energy. They must use safe operation methods and test their products during and after manufacturing. Review question 1. What do you understand by the statement that life would have been very much harder without the chemical industry? Chemical industries provide many of the materials and products we use every day. These products are incorporated in technologies that make modern life easier. Question 2. Name major raw materials used by chemical industries for the production of chemicals. Examples of this include metals like iron, aluminum, and copper, minerals like silicon dioxide, sodium chloride, potash, or other minerals containing boron, bismuth, or lithium, and bigger resources like water, air, crude oil, and wood pulp. Review question 3. Prepare a list of many products which are manufactured by chemical industries. Discuss in groups and give a presentation to the class. Some examples of products that are manufactured by chemical industries include other chemicals that are used in other industries, such as acids and bases and oxidizers, oil and gas, polymers and plastics, coatings and paints, building materials such as cement, food and beverage, so many of the preservatives and flavorings that we have in food, agrochemicals such as fertilizers and pesticides, pharmaceuticals, soaps, disinfectants and detergents, ceramics and glassware, and textiles and dyes. Subunit 4.2, Natural Resources in Industry. By the end of this subunit, you'll be able to define natural resources, list natural resources, and classify them as either renewable or non-renewable. You should be able to define the chemical industry as a firm that involves the taking of raw materials from the environment and turning them into usable products by chemical means. And you should be able to describe the applications of minerals in industry. To begin, natural resources are useful raw materials that we get from the earth. This means that they occur naturally and that humans do not make natural resources. Instead, we can take and modify natural resources in ways that are beneficial to us so that the materials used in man-made objects are natural resources. Natural resources can be classified into two categories. Renewable resources, which are resources that can be replaced by natural processes, which include examples of water, soil, plants, and animals. And the second category, which is non-renewable resources, which are resources that are found in a fixed amount in nature and cannot be replaced. Some examples of these include natural gas, and coal. Any chemical industry utilizes natural resources for its manufacturing activity either as starting materials or other substances obtained from natural resources after processing as a raw material. In summary, a chemical industry is any institution involved in the production of chemicals. They use raw materials available in nature and transform them into desired products by a chemical means. Most of the materials used by industries are present in nature. And natural resources are classified as either renewable or non-renewable. Review question 1. Can fossil fuels be renewed? Fossil fuels are not a renewable resource. They include things like coal, oil, and natural gas and are found in the earth. Review question 2. How can animals and plants be replaced once they die? Animals and plants are renewable resources because they can be replaced through reproduction when other members of the population die. Review question 3. What are natural resources? Natural resources are raw materials derived directly from the earth and are not produced by man-made processes. Subunit 4.3. Production of some important metals and nonmetals. In this video, we'll be going over Part 1, Important Metals. By the end of Part 1 of this subunit, you should be able to outline the extraction of aluminum by the Hall process and describe the main physical and chemical properties of aluminum. You should be able to describe uses of aluminum and outline the extraction of iron by the blast furnace, while briefly being able to describe the conversion of pig iron into steel. You should also be able to describe what wrought iron is and describe the main chemical properties of iron. Furthermore, you should also be able to describe the uses of iron and outline the extraction of copper, while being able to describe the main chemical properties of copper and describe its uses. So let's begin by first talking about aluminum. Aluminum is the third most abundant element next to oxygen and silicon. It does not occur as a free metal in nature, and you can therefore find it in the form of different ores, such as these. If you remember from Unit 3, we saw cryolite and bauxite in the extraction of pure aluminum. So to review that further, aluminum is extracted industrially from bauxite using the Hall process. The Hall process removes contaminants such as silica, iron oxide, and titanium oxide from pure aluminum. In the reaction, powdered ore is heated with sodium hydroxide solution to convert silica into a soluble silicate, and aluminum oxide is converted into a soluble sodium aluminate. We can see these reactions here. The other impurities, such as iron oxide and titanium oxide, are filtered off because they remain insoluble. The solution is then treated with acid to precipitate the aluminum hydroxide, which is shown in this reaction. The aluminum hydroxide is then washed, dried, and heated, forming an aluminum oxide. The pure aluminum oxide is then mixed with some cryolite and then melted. Cryolite is added to our aluminum oxide to reduce its melting point from 2,045 degrees Celsius to 1,000 degrees Celsius. This part of the process should be very familiar from Unit 3. At this point, the molten mixture is introduced to an electrolytic cell to be electrolyzed to obtain pure aluminum. Within the cell, there are graphite electrodes, which are inert electrodes that act as both the anode and the cathode. Through this electrolytic conversion, we get pure aluminum and bubbles of carbon dioxide as a byproduct. Overall, aluminum is a relatively soft, silvery white metal with a relatively low melting point of 660 degrees Celsius. It is a good conductor of heat and electricity, and it can be shaped into wires, rolled, pressed, or cast into different shapes. Additionally, aluminum is a highly reactive metal and it undergoes the following reactions. With oxygen, aluminum will form a thin film and aluminum oxide on its surface. With dilute acids, it will form a salt and liberate hydrogen gas. Aluminum will not react with either dilute or concentrated nitric acid due to the formation of that protective oxide layer on its surface. In chlorine gas, it will burn to form aluminum chloride. And it will also react with sodium hydroxide solution to form sodium aluminate and hydrogen gas. Aluminum is used to make light alloys such as duralumin, a mixture of aluminum, copper, and magnesium. And these aluminum alloys can be seen every day in aircrafts, ships, and cars, the manufacturing of household cooking utensils, to make door and window frames and roofing for buildings, and as packaging material in the food industries and for electrical transmission lines. Aluminum is also used as thermite in the welding process. Powdered aluminum, when mixed with iron 3 oxide and ignited, produces a very high temperature of about 3,000 degrees Celsius. This temperature is quite sufficient for the welding of metals. The mixture of powdered aluminum and iron 3 oxide is called thermite. Now we'll move on to talk about iron. Iron is the second most abundant metal next to aluminum. It constitutes about 4.7% of the Earth's crust by weight, and it is never found as a free metal in nature, much like aluminum. Instead, it is found in the form of compounds such as oxides, carbonates, and sulfides. Some commonly found iron ores include hematite, limonite, magnetite, siderite, and iron pyrites, which are more commonly known as fool's gold. Generally, iron is extracted from hematite, limonite, and siderite, and this process occurs in a blast furnace. Here you can find the overall schematic of a blast furnace. We'll go into more detail about each of these steps, but you should note that the input for the blast furnace is charge, which includes iron ore, limestone, and coke, with molten iron, also known as pig iron, slag, and different waste gases coming out of the furnace.
Iron ore is common in the Earth's crust and contains iron chemically bonded to oxygen. This is mined in places such as the Americas, Australia, and Scandinavia, and then shipped around the world to steelworks. Ores are then blended together to produce a favourable mix. This mix is combined with coke and heated to produce the iron-rich material called sinter. Sintering reduces waste and provides an efficient raw material for the blast furnace. Carbon is required for the blast furnace, and this is supplied in the form of coke. To make coke, coking coal is heated in an oven. This drives off volatile byproducts and leaves carbon. Gas produced in this process is used as a fuel, whilst other byproducts such as tar and sulfur are extracted and refined. These raw materials, sinter, iron ore and coke, meet each other at the blast furnace, where they are fed into the top of the furnace along with some limestone. A hot air blast, from which the furnace gets its name, is injected through nozzles called tuyeres in the base of the furnace. This blast raises the temperature in the furnace to white-hot intensity, around 2,200 degrees centigrade. This very high temperature is needed for the chemical reduction and melting of the sinter and iron ore to form a pool of molten iron in the lower part of the furnace, just above the hearth. The limestone combines with the impurities to form a liquid which floats on top of the molten iron. This is known as slag. The molten iron is tapped from the furnace and the slag skimmed off and taken away for use in other industries, such as road building or cement manufacture. The molten iron we get from a blast furnace, or hot metal as it's known in the industry, isn't pure iron and contains the elements carbon, sulfur, phosphorus, manganese and silicon. To make steel, these elements must be removed or reduced and other elements added, depending on the type of steel being made. The carbon content, at about 4%, makes iron very brittle and unsuitable for rolling or forging. And although iron can be used for castings, most of the iron produced is for processing into steel.
Now that we've seen the overall process of the blast furnace, we can go into the individual reactions that make up the process. First is the oxidation of coke into carbon dioxide. Next is the reduction of carbon dioxide into carbon monoxide. Next is the reduction of iron oxides to metallic iron by carbon monoxide. Decomposition of the limestone by the heat of the blast furnace serves as a flux to remove impurities. Here we can see our calcium carbonate, the main component of limestone, decomposing into calcium oxide and carbon dioxide. The reaction of this calcium oxide with impurities like silica to form calcium silicate or slag allows for the removal of these impurities. As the molten iron flows to the bottom and the slag floats to the top, we can therefore tap off each of them separately. The slag can then be used for further processes such as the manufacturing of cement. The iron obtained directly from the blast furnace is called pig iron. Pig iron contains a number of impurities such as 2% silicon and 1% phosphorus, manganese, and traces of sulfur. The pig iron is then remelted with scrap iron and molded to form cast iron. If most of the impurities is removed from the pig iron, we get wrought iron. Wrought iron is the purest form of commercial iron and has improved strength and malleability in comparison to pig iron. It is manufactured by heating the impure iron with hematite and limestone to increase the iron purity to 99.5%. It's tough, malleable, and ductile. In contrast, pig iron contains a high amount of carbon and makes it very hard and brittle. The purification process of pig iron is carried out in a blast furnace at a high temperature. 3 methods can be used to convert pig iron into steel: the Bessemer converter, the open hearth furnace, and the basic oxygen process. This is the overall schematic of the Bessemer converter. The method by which impurities are removed is through an oxidation reaction and then a further reaction of these oxides with the acid lining within the converter. The process begins when molten pig iron from the blast furnace is transferred into a cylindrical vessel containing a refractory lining of magnesium carbonate and calcium carbonate. A blast of hot air is blown through the molten metal, and at which point the oxygen passing through converts silicon, phosphorus, and sulfur into their oxides. The oxides can then react with the lining to form a slag. The carbon in the pig iron is also oxidized to form carbon monoxide. We'll now talk about our second process, the open hearth furnace. In an open hearth furnace, the furnace is lined with basic oxide refractory, which is magnesium oxide and calcium oxide, and is charged with a mixture of pig iron, iron oxide, and scrap iron and limestone. A blast of hot air and burning fuel is directed over the surface of the charge. Impurities in the pig iron are oxidized by the iron oxide and the air. Carbon dioxide and sulfur dioxide, formed by the oxidation of the carbon and sulfur respectively, bubble out of the mixture as waste gases. Finally, we'll talk about our third process, the basic oxygen process. From this overall schematic, you should note the inputs are molten metal, oxygen gas, and a flux containing calcium oxide. In the process, powdered calcium oxide and oxygen gas are added directly to the surface of the molten pig iron. The oxygen reacts exothermically with carbon, sulfur, silicon, phosphorus, and impurity metals. Carbon and sulfur are oxidized to form carbon dioxide and sulfur dioxide respectively, and these are released as waste gases. The oxides of silicon and phosphorus, as well as the impurity metals, combine with the lime to form a slag. Overall, iron is a gray, lustrous, malleable, and ductile metal that is a good conductor of heat and electricity. It has a high melting point of 1,580 degrees Celsius and a fairly high density. It is a ferromagnetic material, meaning that it can be permanently magnetized. Iron is also fairly reactive and will rust in the presence of air and moisture to form hydrated iron 3 oxide. Iron will also react with dilute acids, forming iron 2 salts and liberating hydrogen gas. Iron also exhibits different oxidation numbers, meaning that it can either have a 2+ or a 3+ charge, designated by the term ferrous for 2+ or ferric for 3+. Iron 2 and iron 3 compounds have different colors, with aqueous solutions of iron 2 compounds having a pale green color, and aqueous solutions of iron 3 compounds having a yellowish brown color. Aqueous solutions of iron 2 compounds are rapidly oxidized into the corresponding iron 3 compounds. And heated iron will react with hydrogen chloride gas, forming iron 2 chloride and hydrogen gas. In addition to chlorine, heated iron will also react with sulfur, forming a sulfide. And iron has the ability to displace less active metals from solutions of their salt. Iron is one of the most widely used metals in the world and ranks first in worldwide consumption. It is used in the construction of buildings and bridges. And as pig iron, it is used to make domestic boilers, hot water radiators, railings, water pipes, castings, and moldings. As wrought iron, it is used in the making of nails, sheets, horseshoes, ornamental gates, knockers, farm machinery, and more. Carbon is also used in the manufacturing of alloys, including carbon steel and alloy steel. Carbon steels are classified as mild steel, which contains up to 2% carbon and is used to make screws, motors, car batteries, railway lines, ships, bridges, and nuts and bolts. The second classification of carbon steels is medium steel, which contains between 0.3 and 0.6% carbon. It's used to make things like springs and chains. Finally, we have high carbon steel, which contains between 0.6 and 1.5% carbon. And it's used to make things like drill bits, knives, hammers, and chisels. Alloy steel contains iron in a relatively higher percentage of other metals. Examples of this include stainless steel, which contains between 14 and 18% chromium and between 7 and 9% nickel. The addition of these other metals allows stainless steel to resist rust. Tool steel includes tungsten steel and manganese steel and are used for rock drills, cutting edges, and parts of machinery that are subjected to heavy wear.